Welcome everyone. In this lesson, we're going to be talking about the idea of continuity. So by the end of this lesson, you're going to be able to determine and explain why a function is continuous or discontinuous, not continuous. And then we'll be able to use this idea of continuity to help us calculate limits. All right, so let's start with the graphical interpretation. We're gonna define what continuity is, but first we're gonna look at the graphical interpretation. And so we have this intuitive definition that says a function is continuous provided its graph does not have any breaks or gaps in it. So another way to think of this is a very intuitive idea, is that when we draw the graph of our function, we can draw the graph without ever taking our pen off the page. So we have this little example here of this function g of x. We have the graph of the function, and try it out. Let's trace over this graph, and when you do it, you never have to take your pen off the page. So let's try it out. Let's trace over this graph, and you can do it in just one nice movement. We never have to take our pen off the page. And specifically, we have this one point indicated, x equals 2. There's no break or jump in our graph at x equals 2. So specifically, this graph is continuous, looks to be everywhere. And in particular, at x equals 2, it's also continuous. All right, so this is just the graphical interpretation. Let's get to the actual definition here. So what is the definition, the limit definition of continuity? So we say a function f is continuous at x equals a, provided the limit of the function as x approaches a is actually equal to the function value directly at x equals a. So there's a few things going on here. So let's first talk about just the left side of this equation, the limit. So if we remember back, we've talked about limits, and what limits are used for is they describe the behavior of our function near as x approaches a, so near x equals a. So that's what this limit does. There's the left side, there's the right side, and then the overall limit just describes the behavior in general near x equals a. On the right side of this equation is f of a, and this is just the function value directly at x equals a. So this really describes the behavior of our function directly at x equals a. So we have this equation, and that's really what it's describing. It's saying the behavior of our function near x equals a is equal to the behavior of our function directly at x equals a. All right, so how do we actually check this though? So we're given a function. How do we actually check that it's continuous at x equals a? Well, there's a few things we need to do. So step one, the function actually has to be defined there. So we need to calculate f of a. It needs to be defined. And this is normally the easiest thing to do, is to figure out if our function is defined there. Then step two is to calculate the limit. So the limit of our function as x approaches a, and we need to calculate this. and that needs to exist. And then we basically compare the results. So our function value has to be the same as our limit value. So then we just compare. And we can really break up this second step, if we wanted to, into left-hand limit and right-hand limit. So instead, we could do the left-hand limit. We're going to have to do it anyways. And the right-hand limit. So we kind of have these three. We'll have these three values in mind. We'll have our function value, we'll have our left-hand limit value, we'll have our right-hand limit value. And for a function to be continuous, these three values all have to be equal. All right, so let's try this out in an example. Example 1. And we're going to see why this idea of continuity is really useful. So in this example, we're given a function that we know this function is continuous at x equals 1. So we're explicitly told here this function is known to be continuous at x equals 1. All right, so we know that. Well, we can use that to help us then evaluate this limit. So let's see what we can do. And why this is such a useful property is to calculate the limit. If we know our function's continuous, we can plug in that x value. So this x value that we're approaching, if we know our function's continuous at that x value, well then to calculate the limit, we just have to plug in to our function. So we can just plug the x value into our function. To calculate the limit. Now, in general, it takes some work sometimes to figure out if a function's continuous or not. But if we know it, well then what we can do is just plug in. So our function here is this natural log function. So we're going to do the natural log, and we're just plugging x equals 1 in wherever we see an x. So we'll get 1 squared plus 4 divided by 5 times the square root of 1 minus 2, which is equal to the natural log of 5 over 3. And so why we can do this, what we're doing right here, is we're just plugging in x equals 1. Just plugging it in right into our function. And that comes from our limit definition of continuity. So the limit definition says the limit of your function f of x, in this case as x approaches 1, is equal to f of 1, provided that the function is actually continuous at x equals 1. And we know that for this particular function because we're told that. So this is what the limit definition is saying for this case here. As x gets closer to 1, the limit of our function is equal to the function value directly at x equals 1. So we can just plug right into our function to calculate this limit. And that's why continuity is so useful. It allows us to quickly calculate these limits. All right, let's see what can go wrong though. So in this example, we're going to look at a few different graphs, and we're going to use the limit definition to determine if these functions are continuous or not. So let's start with the first one here. We see this function, this graph of this function g of x, and First thing we should do is just see what the function value is. So let's calculate f of 2. So we're interested in whether this function is continuous at x equals 2. So let's start with our function value. So we find x equals 2 on our horizontal axis. There we go. And then we just read up until we see the filled in dot to indicate our point on the graph, and we see it right here. And that has coordinates 2, 3. So our actual function value in this case is the y-coordinate, so 3. All right, so that's good. Our function is defined. Now we want to calculate the limit of our function as x approaches 2. And if we look at the graph, what do we see? So as x gets closer to 2, on the left side, it looks like our graph is getting closer to this point right here, which has coordinates 2, 1. So the left-hand limit would be 1. And then if we look on the right side, if we approach from the right side, it looks like we're approaching that same point. So it looks like our graph is approaching that same point, 2, 1. So the right-hand limit would be 1. So overall, the limit of our function, and I guess I should be using g's here because our function is g of x. But if we look at our limits, on either side, we're approaching that same point. So it looks like the limit in this case is 1. And so if we compare these two, they're not equal. So our function value does not equal our limit. So that means we're discontinuous. So this graph is not continuous at x equals 2. We use this word discontinuous to mean not continuous. All right, let's try the next one. So we're given the graph of some function, and let's figure out from our limit definition if this thing is continuous at x equals 2 or not. And again, the way we get started is first just look at the function value. So we want to actually try to evaluate our function. So we find x equals 2 along our x-axis, and then we read up and down to try to find the filled in point that's on our graph, and we don't actually see it here. I don't actually see any filled in dot on at x equals 2. So that just tells us, I see this open dot, but the open dot means it's not included in our graph. So our function's undefined. So we're done. If our function's undefined, then it's automatically discontinuous at x equals 2. And you can, graphically, this should kind of make sense from our intuitive definition. If you were to try to trace over each of these graphs, you're going to actually have to take your pen off the page at each of these points. We have to kind of skip over this open point. We don't want to include that in our graph. So if I was going to trace over this first graph, my pen would go here, and then right before I get to that open dot, I'd have to actually take my pen off the page. Then I'd move it up here, and then I can't go any further there, so I have to take my pen off the page again, and then continue on up here. So I had this kind of break in my graph. Same thing over here. If I was going to try tracing over this graph, I'm okay here, but then I get to this point where I have to take my pen off the page. I don't want to write anything. I want to jump over this point, and then I keep going over here. So in each of these cases, we call these, we sometimes refer to these as removable discontinuities. And the reason is because, if I just I could plug this hole essentially and slightly redefine our function so that we have a continuous graph then. So in each of these, we could if we really needed a continuous function, we could kind of redefine things so that this hole is essentially plugged. Let's look at a couple more. So we have here a graph, and again we're seeing that same kind of behavior, that if I were to trace over this left side, okay, but then I have to take my pen off the page, move it up to here, and then keep going. So there's kind of this jump. So as we'll see, we'll go through the limit definition, but a lot of times we refer to these as a jump discontinuity when they look like this. But let's just see what's actually happening here in terms of the limit definition. So first of all, we want to know, is our function defined? So we find x equals 2. We look up and down until we find the filled in point. There it is. And that point has coordinates 2, 2. So the y coordinate is our function value. So our function value is equal to 2. So far so good. Our function's defined. Now we want to calculate the limit. And we see that there's kind of this different behavior going on the left side versus the right side. So we want to consider the left hand and the right hand limits. So we'll do those separately. So let's start with the left hand limit. So as we get closer to 2 from the left, if we look at our graph, it looks like we're getting closer and closer to this point right here, which has coordinates 2, 1. So the left-hand limit is 1. And then for the right-hand limit, we're going to approach from the other side. So we're going to approach 2 from the right-hand side. And if we go up to our graph, just walk along our graph, see what point we're getting closer to. And it looks like we're getting closer and closer to this point here. So our right-hand limit is 2. And because these two values are not equal, the left-hand limit does not equal the right-hand limit, the limit of our function, the overall limit, does not exist. So our function value is defined, that's good, but our limit did not exist. And so this is discontinuous at x equals 2. And sometimes we call that a jump discontinuity, again, because there's this little jump in our graph. All right, one more. What about over here, this last one? In this case, we'll see what's going on when we look at the definition, but a lot of times we call this an infinite discontinuity, or like an infinite jump, or something like that. And what's going on is, if we try to trace over our graph, we're good over here, and then it just keeps going up and up and up, and eventually I have to kind of take my pen off the page and then kind of jump over x equals 2 and then continue drawing. So there is this kind of, somehow there's this break at x equals 2. And it's because, as we'll see, there's an infinite limit. So if we go through, first of all, our function, is it defined? If I look at x equals 2, nowhere do I actually see a point on the graph. So in this case, it's undefined. It's not equal to anything. So right away we know it's not continuous. But if we were to calculate the limit, it's positive infinity. The left-hand limit is going up to positive infinity. The right-hand limit is going up to positive infinity. So the overall limit, we say, is equal to infinity. So we have an infinite limit, which technically does not exist. So the limit does not exist. Our function value does not exist. No way is this thing continuous. So it's discontinuous at x equals 2. All right, so these are just some examples of functions we might see. Let's try one with a little bit more work here. So example 3, we're going to determine if this function, this piecewise function, is continuous at x equals 20. All right, so it's function c of x equal to 100 plus 12x if our input is between 0 and 20. And the function is equal to 180 plus 8x if our input is greater than 20. So we have this is a piecewise function. And we have these two different pieces. Now we have the graph over here, and you can kind of guess by looking at this graph it's going to be continuous at x equals 20. Yeah, there's a change in the behavior there, but all the pieces match up. So you can trace over this graph without ever taking your pen off the page. So we suspect this thing is going to be continuous, but let's actually show it using the definition, the limit definition of continuity. So first of all, let's start with our function value. This is the easiest thing to do normally. So let's actually figure it out. So we want to plug 20 into our function. And then we just have to decide which piece to use. So we have this piece here where x is less than or equal to 20, or we have this piece here where x is greater than 20. And only one of these pieces works. And it's this one right here where it says x could be equal to 20. So we're going to use that first piece. And what formula do we use? Well, this one right here, this 100 plus 12x. So we're going to use 100 plus 12 times 20, which is 340. If we do the arithmetic. All right, so our function value is defined. That's good. We can keep going. Next, we want to do the left-hand limit. So we need to calculate the overall limit. And for piecewise functions like this, normally that comes down to doing left-hand and right-hand limits. So let's start with our left limit. So we're going to do the limit of this function c of x as x approaches 20 from the left. And we have to decide which piece we're going to use. We have two pieces here to use, and we have to figure out which one. So if we're talking about the left-hand limit, x is approaching 20, but with values that are slightly smaller than 20. So x is less than 20 for our left-hand limit. So we go to the inequalities here, and we figure out, well, which one takes into account values x less than 20. And we see it's this top piece. X could be less than 20, or x could be equal to 20. So if we're interested in the left-hand limit, we need x to be less than 20, and that's what we're seeing right in here. So we're going to do the limit as x approaches 20 from the left of 100 plus 12x. So let's actually fill in what our function is, how our function is defined on that piece. And now this is just a polynomial, so the way we calculate the limit of a polynomial is just plug in. So we have a polynomial, so direct evaluation. All right, that's nice. Polynomials are always nice to work with. All right, so we have our left-hand limit. We have our function value. Now we want to do the right-hand limit. So we're going to do the limit of our function c of x as x approaches 20 from the right. And for our right-hand limit, x is getting closer to 20, but with slightly bigger values. So x is going to be greater than 20. So we have to figure out, go to our pieces here and figure out, well, which piece accounts for x greater than 20. And we see that right here. So for our right-hand limit, we're going to use this piece of our function, this 180 plus 8x. So we fill that in. 180 plus 8x as x approaches 20 from the right. And this is also a polynomial, so direct evaluation works here. So just plug in 20 into this function, and we'll get this limit. And if we do the arithmetic here, we get 180 plus 160, 340. And so what we have here is our function value is 340. Our left-hand limit is 340, and our right-hand limit is 340. So putting these two together tells us that the limit of our function c of x in general, as x approaches 20, our overall limit, is 340. So our function value is 340, our limit is 340, and that tells us our function is actually continuous at x equals 20. Nice. Yeah, that's good. So we checked our function value, we checked our limit, which really had to come down to doing the left and right hand limits, saw that these two values are the same. So because those two values are the same, we can say this function's continuous. And we kind of had an idea that this was going to be continuous by looking at the graph. But if we didn't have the graph, this is the work we would go through. Alrighty, let's try another one. Example 4, we're given this function x squared minus 5x plus 6 over x minus 3. We want to determine if this function is continuous at x equals 3. All right, so again, we want to go to our limit definition. So we want to try plugging in our function. Once we do that, we'll plug in our limit and see if the values are equal. Always, though, a good idea to just start with the function value. So let's look at f of 3. If we were to plug f of 3 in, what would we get? We would get 3 squared minus 5 times 3 plus 6 over 3 minus 3. And that ends up being 0 over 0, which, no good. That's undefined. So it actually doesn't make any sense to plug x equals 3 into this function. We get division by 0, which is undefined. So because our function's not even defined at x equals 3, it doesn't even make sense to actually look at the limit. Or it's not necessary, I should say. So all we're interested in is figuring out if this function's continuous or not at x equals 3. So the limit is not necessary to check. Be good practice. So the limit does actually exist. So it'd be good practice to go through 0 over 0. We can deal with that in terms of a limit. So the limit actually does exist, but our function value does not. So there's a hole in the graph, and our function is discontinuous at x equals 3. All right, let's try another one. Example 5. Given another function, we want to determine if this function is continuous at x equals 3. So again, start with the function value, f of 3. We look. Now this is a piecewise function, so we're kind of given our pieces here. There's this x not equal to 3 piece, and then x equal to 3 piece. And the way we evaluate this function is we figure out the piece, and then we kind of read backwards here to see what the function value is. So at x equals 3, here's x equals 3, we see that our function value is going to be 0. So this is actually defined. All right, so far so good. Now we want to go through and we want to figure out the limit of our function. So we want to do the overall limit of f of x as x approaches 3. Figure out what this is. And again, we have this kind of break in our behavior directly at x equals 3 here. So this is where our piecewise function, the different pieces happen. So to help us deal with that, we want to do the left hand and the right hand limits. So we're going to do our left limit and see what we get here. And then once we do that, we'll do our right hand limit. All right, so let's do our left hand limit. So as we approach 3 from the left. And what this means is if we're approaching 3 from the left, we're using values that are slightly smaller than 3. So x is going to be smaller than 3 here for our left limit. So if x is smaller than 3, when we actually use our function, when we need to decide which piece of our function to use, x less than 3 is covered by this x not equal to 3. So another way to think of this is x less than 3 or x greater than 3. So it's everything except 3. So we're going to use this piece of our function for our left-hand limit. And so we're going to do the limit of 1 over x minus 3 as x approaches 3 from the left. And so when we're presented with a limit like this, first thing we should do is just try to plug in to see what's going on. Gives us an idea of what to do. When we do plug 3 into this, we end up with 1 over 3 minus 3. So we end up with a c over 0 form. So this is a c over 0 form, which tells us it's an infinite limit. So it's either plus infinity or minus infinity. And we need to figure out which. So we have a c over 0 form here. Tells us it's going to be either positive infinite or negative infinite. And the way we decide the sign is with a test number. So, first step for calculating this little limit here is to recognize that we have a c over 0 form, which we just do by plugging in, seeing what we get. Step 2 is just interpreting that. So we know we have an infinite limit now. And then part 3 is going to be test number. So x is less than 3, so we want to pick some test number that's close to 3 but slightly smaller. So, maybe like 2.9. That's close to 3 but slightly smaller. We plug it in. And we get 1 over 2.9 minus, we get 1 over 2.9 minus 3, which is 1 over negative 0.1. And we don't really care about the number, we just care about the sign. And we see that we have a positive divided by a negative, so the result here is negative. So this limit here is negative infinity. Now, the right-hand limit is you can work through it, and you could show that the right-hand limit is positive infinity. But at this point, we've done enough, and this is enough to show that our function is discontinuous at x equals 3. So be good practice. Calculate the right-hand limit for yourself. But at this point, we have enough information to make our conclusion. So since we know the left-hand limit is infinite, our function's discontinuous. It's not continuous at x equals 3. All right. So far our examples, for the most part, we're actually showing that our function is continuous or discontinuous by using this limit definition. Well, the nice thing about continuity is that a lot of the functions we work with, that we're going to be seeing in this course, for the most part are continuous. So most of the functions we deal with are, we'll call them elementary functions. And these elementary functions are continuous on their domains. So as long as we know where the function is defined, we know where it's continuous. So for instance, polynomials, we know they're always defined, so they're defined for all real numbers. Rational functions, which is a polynomial divided by a polynomial, they're also defined for all real numbers with one exception, and that exception is where the denominator is equal to 0. So we can't have division by 0. So rational functions, for the most part, they're continuous, except where their denominator is 0. So that's one thing to keep in mind. Root functions, so the nth root of x, depending on the root, if it's an odd root, well then it's always defined for all real numbers. If it's an even root, we know we can't plug negative numbers into an even root. So just a little note here for the even root. Cannot have negatives. So we're just going through just the usual things that give us issues. No division by 0, no negatives under square root signs, things like this. All right, what about trig functions? Well, sine and cosine, very nice. They're always defined, so they're defined for all real numbers. Tangent, we know, is sine over cosine, so it's defined for all real numbers except where the denominator is 0, so except where cosine is equal to 0. And these values are plus or minus pi over 2, plus or minus 3 pi over 2, and so on. So there's a lot of places where tangent is undefined, but aside from those places, everywhere in between, tangent is nice. It's continuous. Then we have our more common inverse trig functions, so inverse sine, inverse cosine, inverse tan. Inverse sine and cosine are defined on these closed intervals from -1 to 1. Inverse tan is very nice. It's defined for all real numbers, so it's continuous for all real numbers. Same thing for e to the x, our exponential function, defined for all real numbers, so continuous for all real numbers. And then the log function ln x, it's defined for positive numbers, so everything greater than 0. So just a little kind of note here for a log function. We cannot have negatives or 0 inside the natural log. So just a little caution there with our natural log function. But aside from those places, if our log function is defined, it's defined for all positive numbers, well, we know it's continuous there. All right, so all of these sort of elementary function, the building blocks of the functions we look at, are continuous on their domains. All right, so let's look at example 6. We have the limit of h squared plus 2h plus 3 over 4h plus 5, and it's the limit as h goes to 0. Let's calculate this limit and provide some justification based on the continuity of this function. So first thing, when we look at this function, we identify that it's a rational function. So it's a rational function. Polynomial divided by a polynomial. So it's going to be continuous everywhere. The only issue is where the denominator is 0. So we classify it as a rational function. Then we figure out the domain. So it's going to be all real numbers. Except h equal to -5/4. And you could figure that out because at h equals -5/4, our denominator is 0. So our domain is, if we wrote it as an interval, is the interval from -infinity to -5/4, and then the union with the other side, so -5/4 to infinity. So we've just thrown out that place. It's all real numbers except we've removed that place where we have division by 0. It's not continuous there. So what this says, what we're seeing here is we have a rational function. We've figured out its domain, and then the number that we're approaching, h is approaching 0, well, that's actually in the domain of our function. So that's nice. We have a rational function. We've figured out the domain. And then we see that the number we're interested in, h equals 0, is actually in the domain. So putting that all together, this function is continuous at h equals 0. It's a rational function. 0 is in the domain, so it's continuous there. So to actually calculate this limit, we just plug in h equals 0. So we get 0 squared plus 2 times 0 plus 3 over 4 times 0 plus 5, which ends up being 3/5. And again, the justification here is because we have continuity at h equals 0, so we can just plug in to evaluate the limit. So it makes, if we know our function's continuous, it makes it not too bad to actually calculate these limits. All right, so we have that list of elementary functions, but a lot of times we kind of use our usual arithmetic operations to combine them to form new functions. And so we have this result that says if we have a function f that's continuous at x equals a, and another function g which is continuous at x equals a, then we can combine them using addition, subtraction, constant multiplication, multiplication and division, and the result is still continuous at x equals a. So what this result really says is essentially doing arithmetic preserves continuity. So if we have two continuous functions and we add them together, the result is going to be continuous. So nice. Now, of course, there's one little condition here. Addition, there's no issue. We can add two functions all day and there's no issue. Subtraction, same thing. Constant multiplication, no problem. Multiplication, again, no problem there. It's this division. So there is one little extra thing to keep in mind, and that's if we divide one function by another, we can't be dividing by 0. So if we're talking about continuity at x equals a, the function g can't be 0 at a. So we require g of a not equal to 0. If we divide by 0, well then that kind of kills off the continuity at that particular x value, or could. All right, and again, this is just the c here. The c is just a constant, so constant multiplication. All right, so we have our list of elementary functions. Now we know we can combine them using basic arithmetic, and we can produce all sorts of brand new functions that we know are going to be continuous as well. So let's look at this one. Example 7, we're going to figure out where this function is continuous. So 3 times natural log x plus inverse tangent x, all divided by x squared minus 1. We want to figure out what x values is this function continuous on. So essentially, we see that it's the combination. There's addition, there's division, there's subtraction. But essentially, this is the arithmetic combination of some of our elementary functions. So we have a log function, we have an inverse tan function, we have a polynomial. We've just combined some of our elementary functions together with basic arithmetic to produce this brand new function. All right, so let's kind of go through and just identify the different pieces of this function. And to kind of help us, not absolutely necessary, but let's rewrite this function just slightly. We're going to write it as 3 times natural log x plus inverse tangent x times 1 over x squared minus 1. We're just going to look at all these different pieces here and figure out where they're continuous. So let's kind of keep track on a little table. All right, so let's start with the 3 times natural log x, or actually just natural log x. Where is just the natural log x function continuous? Well, it's continuous on its domain, and its domain is all positive numbers, so the interval from 0 to infinity. Now, if we take that function and multiply it by a constant, in this case 3 times the natural log function, that constant multiplication doesn't change where this new function is continuous. So this new function, 3 ln x, is also going to be continuous on the interval from 0 to infinity. Okay. What about inverse tangent? Where is inverse tangent continuous? Well, if we go to that table, that elementary table, it's continuous for all real numbers. So on the interval from minus infinity to infinity. Okay. So now we have this piece here. We know where it's continuous. We know where inverse tan is continuous. And if we add these two together, we get a brand new function, 3 ln x plus inverse tangent x. And we kind of have to use the numbers that appear, since we're adding these, we have to use the x values that appear in both of these intervals. So yeah, inverse tan is defined for negative numbers, but natural log isn't. So if we were to look at their sum, 3 ln x plus inverse tan, it's not going to make any sense to try to plug a negative number into this whole thing. So we kind of have to go through and just use the x values, use the numbers that show up in both of these. So when we do that, we end up with the interval from 0 to infinity. So we know where this sum is continuous. Okay. And then what about, all right, so that takes care of this first major piece of our function. Then we have this 1 over x squared minus 1. This is a rational function, so we just have to figure out where do we have division by 0. So it's a rational function, so that means it's defined, it's continuous for all real numbers. and then except where the denominator is 0. So in this case, if we were to set x squared minus 1 equal to 0, we would get x is equal to plus or minus 1. So we have to throw out x equals negative 1 and x equals positive 1 because this function's not defined there. But everywhere else, perfectly good. So again, just to be careful here, no division by 0. All right, so then putting it all together, we have this 3 ln x piece plus the inverse tan. And then we want to multiply it with this rational function. And so again, we have to go through and only use the numbers that appear in both. So we have this interval here from 0 to infinity, and then for this first piece, and then for this second piece, it's everything except positive 1 and negative 1. So from the first interval here, we have to throw out all the negatives and 0. So our domain here is going to start at 0. And then if we kind of move along the x-axis, we have to throw out positive 1. And then everything else is okay. So basically, we look at this interval here, and we're just deciding which numbers show up in both of these. So 0 to infinity shows up in here, but then we have to throw out positive 1. So this function is continuous on the interval from 0 to 1, union with the interval from 1 to infinity. All right. Let's try another one. And we're going to use that continuity then to help us calculate this limit. All right, so let's kind of go through the same type of analysis here. We have the function here is sine x divided by 1 plus cosine x. And we're interested in the limit as x approaches pi over 2. So what we want to do to make this easy to calculate, we want to know, is this thing continuous at x equals pi over 2 so that we can just use direct evaluation. That would be really nice. If we know this function's continuous at x equals pi over 2, we can just plug in then to calculate this limit. So let's go through and figure out where this function's continuous. Kind of go through the same type of analysis we just did. So we'll kind of write out the different pieces of our function, and then we'll write out the intervals where they're continuous. All right, so first of all, we have sine x on top, so let's look at that piece. Trig functions are nice, so sine and cosine are nice. They're defined everywhere, so this thing is continuous everywhere. So it's continuous on the interval from minus infinity to positive infinity. What about in the denominator? We have 1 plus cosine x. So here we have the sum of two continuous functions. Cosine is always continuous, and the constant function 1 is always continuous. So we have the sum of two continuous functions here. So each of those is continuous on the interval from minus infinity to infinity, so their sum is also continuous there. All right, so what about when we do the quotient? Sine x divided by 1 plus cosine x. Well, it's going to be continuous everywhere, except we have to be careful. We're dividing, so we can't have division by 0. So it's going to be continuous on the interval from minus infinity to infinity, except where 1 plus cosine x, except where that's equal to 0. So it's helpful to figure out where this happens. So 1 plus cosine x, where does this equal to 0? Well, if we solve for the trig part, we get cosine x is equal to -1. And we should know where this happens. This happens at x equal to plus or minus pi, plus or minus 3 pi, and so on. So those odd multiples of pi. All right, so this sine x divided by 1 plus cosine x, it's continuous everywhere except where we're dividing by 0. And we're dividing by 0 at these x values here. But for this problem, we're really interested in x equals pi over 2. So we've just shown that this function is continuous at pi over 2 because the only place we're getting division by 0 are at these odd multiples of pi. So we've just shown through all of this is that our function is continuous. It's continuous for all real numbers except for these multiples of pi. And really all we're interested about in this problem is at pi over 2. So how do we calculate this limit? We just plug in. So we get sine of pi over 2 over 1 plus cosine of pi over 2. We're just plugging in. And then these are some of our important angles. So sine of pi over 2 we should recognize as 1. And then cosine of pi over 2 we should recognize as 0. So we get 1 plus 0, which ends up being 1. All right, so knowing that our function is continuous really simplifies this limit calculation process. All right, so we have our list of elementary functions. We know that we can add, subtract, multiply, divide, with maybe some exceptions here with division, and still get something that's continuous. Well, there's other ways to combine two functions. And so another way to combine two functions is with what we call composition. So given two functions f and g, the composite function f composed with g is defined by this formula here. So we're going to form this brand new function, this composite function, and the way we calculate it is our input is x, we plug that into g first, and then we plug that into function f. So a lot of times we call f the outer function here because it's the last thing that happens. And then we call function g here the inner function because it happens first. So when we talk about these composite functions, a lot of times we use the terminology inner function, outer function. And when we do composition, the order matters. So we're maybe used to addition and multiplication where it doesn't really matter what order you do things in, but with composition, the order actually does matter. So in this definition, f composed with g, g happens first, then f happens second in that specific order. So the order does matter. All right, so let's just do a little example here and calculate. We have two functions, f of u, arcsine, which is the arcsine function, arcsine of u. And then we have this other function, u of x, which is 1 minus the square root of x over 1 minus x. And we want to calculate that composite, f composed with u. And let's actually get a nice formula for this. So the way we do this is we're first going to plug our input x into that function u. Then we'll get a result here, and we'll plug that result into our outer function, so our outer function f. All right, so let's fill in what u of x is. It's this fraction. So we're going to take 1 minus the square root of x divided by 1 minus x, and we're going to plug that whole thing, this whole fraction, into our function f. So if I go to my function f, wherever I see a variable, I'm going to plug this whole thing into that variable. So our function here is arcsine, so I would end up with arcsine, or inverse sine, of this whole fraction. So 1 minus the square root of x over 1 minus x. That's how, little example for just getting practice with these composite functions. Probably something you've seen before, but it's good to just recall this. And so this is another way to combine two functions, and so continuity also works really nicely with this composition. So we're going to have two results dealing with continuity. So our first result here is if we're dealing with a composite function, so f composed with g, if the limit of that inner function is equal to b, and that limit exists, and we know our outer function is continuous at x equals b, well, what we can do then is to calculate this limit of this composite function. Essentially, we can bring the limit inside that outer function. So that's kind of what this theorem says. We can bring this limit inside. So our outer function here is continuous at x equals b. Then if that's the case, then we can actually bring the limit inside and do the limit of our inner function first. All right, so if we know and that's all because we know our outer function here is continuous. So if our outer function is continuous, we can bring that limit right on through and do the limit of just the inner function. So it just simplifies a little bit of the complexity in terms of calculating limits. So let's try an example, example 9. We have this composite function we just calculated, arcsine of 1 minus the square root of x over 1 minus x. We want to calculate the limit of this as x goes to 1. So the first thing we should think is, let's identify our outer function, which is arcsine in this case. And what we want to do is we want to be able to bring this limit inside the outer function. To really help us simplify this down to something that we can kind of immediately work with. So 1 minus square root x over 1 minus x. Now we can't just do that. So there is a question mark here, and we have to come back to it. So we need to know, is this continuous at whatever value we get when we calculate this limit? So there's a question mark here with this step. We really can't do this step yet without further investigating this inner limit. So let's actually do that. Let's actually look at the inner limit. So we're going to do the limit of 1 minus square root x over 1 minus x as x approaches 1. Now, first thing we should do when we're presented with a brand new limit like this is just to try to plug in, see what you get, so that you kind of have some idea of where to go with your work. So when I plug 1 into this, I get 1 minus the square root of 1 divided by 1 minus 1. I get 0 over 0. So this is a 0 over 0 form. So that means we have to do some kind of additional work. We have to use some algebraic methods to help us calculate this. And what we see is we have this square root function. So we have a method that helps us when we have root functions like this. We called it the conjugate method. So what we're going to do is we're going to multiply by a fancy 1. So we're going to multiply the top by the conjugate of the 1 minus square root term. And then if we do that to the top, we also have to do it to the denominator there to keep things balanced. If we multiply out the terms in the top here, we end up with 1 minus x. And I'll leave it for you to actually kind of go through the FOIL there, the multiplying out. But you should end up with 1 minus x. And then in the denominator, we're going to have 1 minus x times the 1 plus square root x term. We're doing the limit as x approaches 1. Now notice here we have 1 minus x here. We have a 1 minus x here. So those cancel. Those factors cancel. And we're left with the limit of 1 over 1 plus square root x as x approaches 1. And as soon as we do our canceling, we should try to plug in again. So if we plug x equals 1 into this function, we end up with 1 over 1 plus square root 1, which is 1/2. Now, why can we plug in like this? Is, again, this new function, 1 over 1 plus square root x, this is continuous at x equals 1. So there's no division by 0. No negatives under the square root sign. And what we have is we have a constant function 1, which is continuous. We have the sum of two continuous functions here, and we're dividing, and there's no division by 0. So this thing is continuous. It's kind of a arithmetic combination of our elementary functions, so that it's no division by 0, so it's continuous. So the way we calculate that limit is by direct evaluation. We just plug in. We get 1/2. And so we need to know, going back to our original limit, we need to know, is arc sine, is inverse sine continuous at this x value, 1/2? And go back to our list of elementary functions. We see inverse sine right here. And yeah, it's continuous at x equals 1/2. So yes, it is. Good. So we were okay in doing that step. We know arc sine is continuous at x equals 1/2, so this was correct. We could actually bring the limit inside, and now we know what this limit is, so let's actually just fill it in. It's 1/2. So this whole thing ends up being the arc sine of 1/2. Nice. All right. Well, there's one other result regarding the composition of two continuous functions. So again, if we have two functions, we know the inner function is continuous at x equals a, and we know the outer function is continuous at g of a. Well, then their composition is also going to be continuous at x equals a. So this is just another result basically saying the composition of two functions is continuous. So the composition of two continuous functions is continuous. So continuity works really nicely with composition. So if we have two continuous functions and we form their composition, well, then the result is going to be continuous as well. So let's just try a couple examples where we figure out where these functions are continuous. So in part A, we have the function h of x equal to sine x cubed. We want to figure out where this thing is continuous. And this is really the composition of two functions. So we have an outer function, which is really the thing that is done last. And that's going to be this cubed. So our outer function here is u cubed. And our inner function is the thing that happens first to our x. So when we plug x in, the very first thing that happens is then it goes into the sine function. So we'll call that g of x, or u of x. It's going to be sine x. So if we calculated f composed with u, we would essentially take sine of x and plug it in for u here. We'd end up with back to where we are, sine of x cubed. So this is a helpful skill, being able to break apart a composite function into its outer function and inner function. And sometimes there's more than one way to do this. But if we think about then each of these pieces on their own, the cubed function is continuous on the interval from minus infinity to infinity. And so this puts no restriction on what's happening with our inner function. So any number that our inner function spits out, our outer function is going to be continuous there. So there's no restrictions. And then if we think about our inner function, sine x, well, sine x is continuous for all real numbers as well. So if we have this outer function, which is continuous everywhere, our inner function is continuous everywhere, when we put it all together, the composite function, sine of x all cubed, is going to be continuous everywhere as well. So h is continuous. On the interval from minus infinity to infinity. All right, so good. That composite function, each of the outer and inner pieces alone were continuous everywhere. So when we kind of combine them, the result is continuous as well. All right, let's look at this in part B here. Let's look at this other function, capital F of x. It's the natural log of 1 plus cosine x. And we want to identify, we want to try to break this function apart into an outer function and an inner function. And then we're going to look at each of those pieces and see where they're continuous. And you know, when you look at these, if you see a set of parentheses, usually what happens is what's inside those parentheses, that's the inner function. So we have 1 plus cosine x. That's going to be our inner function. So let's call that u of x. That's going to be 1 plus cosine x. Now, as it is, this thing is continuous everywhere. So this takes on, you know, this perfectly continuous everywhere. But what happens is we're going to then take that result and we're going to plug it into our outer function, which in this case looks to be everything that happens outside, which is the natural log. So let's call our outer function natural log of u. And we know that the natural log function, it's not all real numbers like we had with u cubed. there's some restrictions here. So this is continuous on the interval from 0 to infinity. So we can't have negative numbers inside the natural log function, and we can't have 0. So only positive numbers. So there is some restriction. So our outer function is kind of putting some restriction on what our inner function can do. So by itself, the inner function here, there's no restrictions with our inner function. Where the restrictions are happening is with this outer function, natural log. So we need this inner function to be greater than 0. So we need 1 plus cosine x to be greater than 0. Otherwise, that composite function is undefined. Can't plug a negative, can't plug 0 into the natural log function. And we've actually investigated this 1 plus cosine x. 1 plus cosine x is equal to 0. We went through this before in a previous example. And what did we see? At x equal to plus or minus pi, plus or minus 3 pi, and so on. And that's as small of a value as this 1 plus cosine x gets. So cosine x, the smallest cosine gets is -1. So the smallest 1 plus cosine can get is 0. So this expression 1 plus cosine x is actually never negative. So the only issue is these places where 1 plus cosine x is equal to 0. We can't plug a 0 into the natural log function. We can't plug negatives in, but 1 plus cosine x is never negative. So where is this composite function continuous then? Well, it's continuous on the interval so we need to kind of start with our real numbers. So we'll write this out a few different ways. We could write it as the real numbers, and then we have to throw out these places where that inner function makes our outer function undefined. So we have to throw out these x values here. So plus or minus pi, plus or minus 3 pi, and so on. So there's no limit to what we plug into 1 plus cosine x. So that's why we can start with our real numbers. Or another way to think of that is just the interval from minus infinity to infinity. So there's no restriction on our inner function. So we can plug in anything based on just our inner function, but our outer function then makes this additional requirement that we can't use these values, because then we get 0. We can't plug 0 into the natural log. So this is one way to write it, all real numbers. Another way to write this is, we'll write it out a few different ways. We could write it as minus infinity to infinity, where we throw out these x values, so plus or minus pi, plus or minus 3 pi, so on. So you might write it like that. Or you can write it in, well, there's too many x values that we're throwing out. So let's just write it as that. So minus infinity to infinity, where we throw out plus or minus pi, plus or minus 3 pi, and so on. And there's probably more ways to write this, but that's fine. All right, so continuity is a very useful idea, as we kind of saw, in that it allows us to really, if we know a function's continuous, we can quickly calculate the limit of a function. And so in a lot of applications, we want to know, is our function continuous? And as we've seen, a lot of our usual arithmetic, if we have two continuous functions, if we add them, subtract them, multiply them, divide them, multiply by a constant, or do their composition, the result is still going to be continuous. So we have all of those elementary functions, the kind of the building blocks, and then we can combine them using all sorts of algebra and still get a continuous function, with some exceptions, of course. All right, so that's going to do it for continuity. In the next lesson, we're going to talk about a brand new type of limit, and that's limits at infinity. So we'll see you then. Bye-bye.